Hello, everyone. This is Spencer Snowling from Hatch, and thank you for joining us today for the latest in our ongoing webinar series about GPSX. Today, I'm going to be talking about modeling temperature effects in the activated sludge process using GPSX. So, as per usual, I'll be showing some slides and I'll be doing some desktop demonstrations. So, if you have any questions that you think of along the way, please feel free to type those in the chat. And when I get to the end of the webinar, we'll take a look and I'll answer a few of those live at that time. All right. So my plan for today is to talk first of all about the actual temperature settings that are available in GPSX. As you'll see shortly, that there's a couple different ways you can go about controlling the temperature. And for that purpose, I thought I would cover sort of what your options are and how to set that up. And then I'm going to talk about the biological, physical, and chemical effects of temperature on the processes in the activated sludge system. And we're going to run some desktop demonstrations. We're going to do sensitivity analysis as one of the things I always like to do in these webinars. And then at the end, of course, we will do some questions and answers as always. Right. Okay. So for the most part, temperature is an input in GPSX. It is not an output. It is not a thing that is predicted for you. It is something that you enter in and set constant, or you may read it from a file in order to be able to, drive some of these temperature-dependent changes. You may want something to dynamically change over time, or you may be just choosing a particular design temperature, and so you're going to set that and run with it from there. So many of the input parameters that are used in the biological and chemical reactions are temperature dependent, meaning that whatever is the number that you enter into the software, that number then gets subsequently corrected or adjusted for temperature as well. And so there's some of those that you can see here, the biological constants. I'm going to talk about that in a moment. Diffusion constants are another example, the acid-base dissociation constants. All of those change automatically. Even though you can set them, they automatically get adjusted further for the temperature. So some physical properties of other things are also temperature dependent. And we do have one exception to the rule. We do have one specific case in our models, one of our unit processes, where we do predict the temperature. And I'll come back to that at the very end of the webinar today. Okay, so as I mentioned, we have two different ways of setting the temperature in your layout. We have the global setting, and then we have a local setting. So the global temperature setting is essentially one single temperature for the entire plant. So it is going to be used by all of the different unit processes in the layout, meaning that it is a constant across the length of the treatment process. So that is accessible right here from that pin in the upper left-hand corner of your drawing board. This is the Site Properties menu. And when you click on that, it brings up this menu for you, and it has many tabs. And if you go to the Plant-Wide Properties tab, this is where you will find the liquid temperature. And it will be 20 degrees Celsius by default in all of our libraries. So you can make a change here, and that will be applied across the whole plant, across all of the individual unit processes if you're using the global temperature setting, which is, by the way, the default is to use global. Now, there's the local settings, which is a place where you can have an individual temperature that basically overrides the global value. So for one particular unit process, you can set a value that would be different than the global. And if you want to have a sort of tapered temperature as it goes across, or maybe something that might increase as it goes across the entire length of the treatment system, then you would do this for each one of the individual unit processes. And almost all of those menus can be found under input parameters in the physical menu, the very first one at the top. And then if you go to the More button, you will find that you will get to this menu where you can turn on, use local settings for oxygen solubility and biological activity. It's basically saying, I want you to use the local settings from this menu, not the global ones. And you'll find just below that, when you turn that on, this part below will become active, and then you can set that local temperature there. So now I did notice Um, that here I'm mentioning the local temperature and then also the blower inlet temperature. I will mention this while I'm here, even though this is part of the physical effects. This blower inlet temperature here is used in calculating the density of the air. So if you really want to make sure you're doing, a fine level of calibration on your airflow, you may want to come and set this as well. Okay, moving on. It is quite common to read the temperature, the liquid temperature, in from a file during long simulations, especially if it's something where you might want to reflect the change that happens just normally with your regular influent flow due to the changing of the seasons. This is particularly a big effect if you happen to be located somewhere where it does get quite cold in the winter, such as where I live. We range between quite warm and quite cold temperatures here. And so you might see some data like this. This is actually from one of our projects. You can see that it goes, ranges between, almost 25 degrees Celsius all the way down to somewhere, between 10 and 15 or even closer to 10 during the winter. So that, of course, is quite a big swing of liquid temperature. So you're going to see, a fairly big swing of effects within the system as we're going to go through and talk about those shortly. So now I do want to mention, just to be clear, that what we're talking about when we're setting these values is the liquid temperature, not the air temperature as you might collect from a weather forecast. So you can say it's 22 degrees Celsius, so your wastewater temperature might be different than that. My experience over time has been, for a lot of the project I worked on, that the liquid temperature tends to be a little bit colder than the air temperature, although it really does depend on your collection system and how the the wastewater gets to the plant and the physical geography and so on of your area. So just keep in mind we're talking liquid temperature here. Hopefully that's something that you might have some data for. And I do recommend that if you're doing the local temperature settings for each individual object, you try to remember to set it for all of them as you go along. Because otherwise, if you don't, then it will use the global setting for the ones that you're not, and that would be probably left at the default of 20 degrees Celsius. So it's up to you. Both ways work. Whatever works for you, go ahead and do that. Okay, so that's how you go about controlling the temperature in GPSX. And for a lot of the design type work that people do or analysis, you're generally going to pick a temperature and stick with it. You may I've seen lots of instances for design work where people want to run at sort of like a summer temperature and then a winter temperature. So they might have different scenarios to do those things. So you might find that that's the way that works best for you too. Okay, so let's talk now about how the model responds to those temperature values that you have provided it. So as I mentioned, I'm going to cover biological and then the physical and then chemical aspects of all of these changes. So here, let's start with the biological. Now, the very obvious and probably the biggest effect that you will see in all of this for the activated sludge process is how the biological, how the biomass changes with the temperature. So basically, as I'm sure you're aware, when it's warmer, the biomass is going to grow faster. So this is made to work in the model through the use of the Arrhenius equation. So I'm sure you've seen this probably before in some design class or design approaches. You have a relationship here that says, I'm going to start with the temperature growth rate. So this would be your maximum specific growth rate for the biomass. For each of the biomass types, you're going to start with a growth rate here at 20 degrees Celsius. Then we're going to multiply it by some temperature coefficient to the power of T minus 20, where T is the temperature. So the idea here is this theta value will probably be just a little bit greater than 1, so that when T is greater than 20, this is going to increase this value of the growth rate when T is higher, and it's going to decrease it when it goes lower. So it seems that it's a very straightforward, sort of exponential relationship here, and it works really well. It's totally valid for, the experience that we have is we generally kind of say sort of like, 5, 8 degrees Celsius, something in that neighborhood, all the way up to 30. There's reasons why above 30, it might be a little bit over predicting the growth because At some point, the high temperatures become inhibitory unto themselves. And as we'll see later on, there's a double Arrhenius equation that we use in certain places. So anyway, but for like, let's say 10 to 30 degrees Celsius, this thing works great. Okay, so what this means then was when you're using GPSX and you open up the input parameters and you're looking at the kinetic menu, so you right click on any of the bioreactors, go to the input parameters menu, go to the kinetic menu, and you see a menu that looks like this. As you may recall, this is a very long menu. We have a large number of biological parameters for there's a set of like 6 or 8 or 10 of them for each one of the biomass types. These are values for 20 degrees Celsius. So that means that if I go back to the equation again, that's this value right here. So we're going to take that value and we're going to correct it for the temperature. So you'll see the default values here. And of course, you may have come to this menu and made changes to this in the past for the purposes of calibrating your model. Then, if you slide all the way to the bottom of that menu, and as I mentioned, it's a long one, so you got to slide all the way down to the bottom, you will find the temperature coefficients that are used for the various parameters. Now, there's not one for every single parameter. Some parameters we don't correct for temperature, but a lot of the growth rates, decay rates, COD storage rates, various things, those are being corrected for temperature, and you can see those here. So as I mentioned before, you can see that a lot of these are just a little bit above 1. The higher the value here, that means it's more sensitive to the temperature. And so you can see some of these values here. So this specific absorption rate is actually 1.0, meaning that we have the ability to correct that one, but we're not currently doing that under default settings. But if you wanted to, you could come in and change that number. So just to reiterate one last time, in that equation, that is this value right here, this theta. So, okay, so we have all of this. You can come and make those changes if you like. What you're basically saying is we're controlling the sensitivity of each one of these parameters to a change in the temperature. Okay, so how does this look then? What does this look like when we apply this correction? So what I've plotted here is the heterotrophic maximum specific growth rate in blue and the aerobic decay rate in orange there versus temperature. Now what I'm plotting here is just the value of the temperature corrected coefficient. So that gets applied in the model, and then a whole bunch of other stuff is multiplied by this. But for the most part, you can see here that, of course, as we go to higher temperatures, we get higher values of the growth rate and higher values of the decay rate. And we can see here that the growth, of course, grows faster than the decay does. So that's, of course, normal. It's a lower value. And the difference between these two, as you may remember from that previous slide there, the growth rate is more sensitive because it has a higher value, 1.072 versus 1.029 for the decay rate. Now, I'm plotted again, that same information here, the maximum specific growth rate of the heterotrophs in blue. And I also plotted alongside these the AOBs and NOBs, ammonia oxidizing biomass and nitrite oxidizing biomass, from our Mantis 2 model under our default settings here. And you can see that, of course, those two nitrifier types here are, very similar in magnitude and so on. But I did want to point out the fact that they have different values to start with. Under our default settings, we'll see the NOBs have the slightly higher growth rate than the AOBs do. That is, of course, does make sense. It's a two-step process. The AOBs take it to nitrite, and then the nitrite oxidizers take it to nitrate. So you certainly want the second step in that process to be faster, otherwise you get a lot of accumulation in the middle. But speaking of that problem, if you look over here to the right, the NOBs don't actually increase quite as fast as the AOBs do, and they actually cross over each other here around 28 degrees Celsius. So that's something to keep in mind. Now, this doesn't necessarily mean you're going to get nitrite accumulation once you get up to 28. It's a function of many other things, such as what your DO is and the SRT, and the sensitivity of these two biomass types to oxygen and so on. But I will mention it. It is sort of a feature of the way that these things have been calibrated over time. I have actually worked on projects where nitrite accumulation was the whole point of what we were trying to do with the modeling, and this effect is there in order to be able to predict that when it is relevant. Okay, so time for a desktop demonstration. So this is always the part of the webinars I enjoy the most. Okay, so what I'm going to do is I'm just going to really quickly explain this activated sludge process here. So let's pretend this is a very small, kind of a very simple extended air plant here, no primary clarifiers. And I'm just using the regular default settings in GPSX here. So that's kind of like regular North American municipal wastewater. And we are then going to go into a plug flow tank here, and you can see that there's those 4 reactors as normal, a secondary clarifier, and then the overflow from there is going to go out to this outfall. So I have a DO controller on in this aeration basin that's going to hold to 2 milligrams per liter for all of those 4 passes. And I've kind of set this up with, to give us a reasonable mixed liquor and a reasonable SRT. So I'm going to run this for steady state. And we can see if I'm just looking at this tab right here, this is the concentrations in our outfall. And we can see right away that our BOD is like 4.6 and our ammonia is 0.16. So that means we're doing full BOD removal, full nitrification. I didn't bother with setting anything up for phosphorus here, since that's kind of not the point of what I was trying to show. So just assume we're not removing any phosphorus. Okay, so what I want to do then is I want to run this at some different temperatures. So what I've already done is I opened up this plant-wide properties menu, and here's that liquid temperature. So I clicked on this little button here, plant-wide properties. I've already dragged that up there. So now we have the opportunity to play with the temperature and see that how that affects things. So we'll take a look at how it's going to affect the nitrification and a couple of the other key, sort of biological process indicators that you might want to keep an eye on. So just a quick explanation of these that I set up ahead of time. I'm just going to look at nitrification. That's, for argument's sake, the thing that I'm most interested in here. So I'm looking at DO in red. We can see it's exactly 2 milligrams per liter in each of those 4 passes as we go from the upstream to the downstream side of that bioreactor. It's doing its job. And then we can see here the ammonia, which was, I believe, 28 coming in, is down to sort of 5, and then all the way down to, what do we got here at the end? 0.16. It's the same thing that's in the effluent because it doesn't change going across the clarifier. Okay, so full nitrification, and as you can see, well, we have a little blip here of nitrite, but that mostly gets oxidized to nitrate, and here's our accumulation of nitrate, and it's all the way up to 18 by the time we get to the end. All right, so we have lots of opportunity here to sort of play and see the sensitivity of this. So let's go cold first. I'm going to slide this all the way down here to 8 degrees Celsius, and I'm going to run it again. So now this is a steady state solution, by the way, meaning that this is what it would be like if the plant ran for 2 or 3 weeks at 8 degrees Celsius. So we're going to assume this is really cold. And as you can see, we're now only partially nitrifying. In fact, it's not going all that well. Our effluent ammonia is like 6. And as you saw, all of those lines came up. We're still supplying lots of oxygen. We're still wasting the same amount. We still have, we have 5 days of SRT in this particular example. So what we're seeing here is that, of course, the AOBs and the NOBs are growing more slowly because we've corrected that growth rate down due to the colder temperature. All right, so let's jump all the way up to the top. Let's go 30 degrees. And so it's now really hot. All the bugs are super happy. And we're doing, complete nitrification down here to less than 0.1 in our effluent. So obviously, it's kind of a nice way to sort of get the sense of what's going on here, full nitrification and so on. So there's a few other things that are going to be going on in here as well. I'm going to switch over to this tab, and I'm going to do that again one more time. So let's run it at 20. And we can see that our mixed liquor here is at 2268. and our airflow is at 22,000 meters cubed per day. So let's go back and do it in the cold weather again. So if we run that, so this is now taking into account the fact that what effect it has on all of these other parameters. So our mixed liquor is up, which is as you would expect for colder weather, a little higher mixed liquor. And we can see here the total airflow went from 2,200 down to 22,000 down to 16,000. And then if we go all the way up to the hot temperature again and run that, we'll see, of course, that it went from 22,000 to 24,000, and actually our mixed liquor goes down. So the higher the temperature, the lower the mixed liquor, and so on. So these are kind of like straightforward relationships, but they're there, and I sort of wanted to isolate them in terms of everything else, so that you can sort of see those effects. Probably, or at least for me anyway, the easiest way to see this effect is to run a sensitivity analysis. So this is the effluent ammonia, nitrite, and nitrate that are going to be in this outfall. And we're going to plot those versus the temperature. And now I'm going to use the scenario, the analyzer feature here. So I'm going to flip over to a scenario that I set up ahead of time called sensitivity analysis. And you'll note here that this has now been changed to an analyze step function, and that we're going to turn on the analyzer. I'll just pause here one moment to say, by the way, this is a new feature that is a part of version 9 of GPSX, that you can save the properties of your inputs up here as a function of your scenario. So I just did that to be able to show that off. So that way I don't have to come in here and set the min and max and delta and all that. It's already saved as I need it. Okay, going to turn on the analyzer. And then now, you can see here that we're going to run from 5 degrees Celsius up to 20 degrees Celsius, and we're going to do a steady state, and we're going to run those one after another, and we're going to see what kind of results that we get here. All right. So this is a typical type of sensitivity analysis you might do on temperature. And so just to interpret what we're looking at here is the ammonia here is in this kind of orangey color or yellow color here. And we can see that it is high up at the top, all close to 25 milligrams per liter when we're at the very low temperatures. So what that means is, of course, that means that we're not nitrifying at all. When we're in those very lowest temperatures there. So nitrite and nitrate are 0, and ammonia is pretty much at the max. So it's coming in the front end of the plant and basically not being reduced at all. Then we kind of hit this 8, 9, 10, 12 degrees here, this slope. And what's happening here is we're getting partial nitrification. And during the first part of that, when it starts to get warm enough, you can see actually the light green line here, that's the nitrite. So there's a point here where we have ammonia and nitrite. Meaning that it's only partially nitrified. It's only taking that first step. And then eventually we get warm enough that that can be fully nitrified. So the nitrite goes away because it is being, fully oxidized over to nitrate. And then as we keep going to warmer and warmer temperatures, we're just kind of polishing off the rest of it all the way to the end. So this is kind of a cool way to sort of analyze the way your nitrification is going to work. It's kind of like, what is the minimum temperature required to be able to nitrify under these particular situations. You can plot graphs like this to be able to see how that is going to work. Now, granted, like any other sensitivity analysis you do, I left everything else the same, so I was wasting the same. The DO was always 2 milligrams per liter, and so on. So all of those things were there. They were part of this sort of assumptions buried in this type of analysis. But it's something interesting to sort of take into account. Okay, so let's go back to the slides. Okay, so that's kind of all I had really to say about the biological aspects. Now, just keep in mind that there are 10 different biomass types in the Mantis 2 model in GPSX, and they all have their own calibrated temperature parameters and so on. So once those things kind of start to interact with each other and some of the other aspects that you have, sometimes the temperature effects can be really interesting to play with and to dig into the details. All right, so the physical temperature effects, and what I mean by that is sort of the not biological part, the part that's related to like the physical components of the system, the mechanical parts and various other things. the mass transfer and so on. So the one main one that is, really quite the most significant part of it, which is the aeration system. That is the one that's probably the most important when it comes to thinking about how that is affected by the temperature. So first of all, water properties, various water properties are going to be temperature dependent, like density and viscosity and so on. The big one is the gas solubility in water is a function of temperature. And so are a lot of the mass transfer coefficients, they're corrected for temperature as well. And related, of course, diffusion constants. In this case, I'm specifically referring to the ones in biofilm. So we're going to take a look at each of those things kind of separately unto itself. So just starting with the water properties, this is also a relatively new thing in GPSX that we broke out some of the calculations and made a menu here for you to look at if this is important to you. So at any connection point, you can right-click, go to Output Variables, go to Water Properties, and you'll open up this menu, which basically gives you the details of the density and the viscosity and various vapor pressure and other things. Not all of this is sensitive to temperature, but density and viscosity is. So you will see those change. These values are used in various places for various things. I guess the most significant one that I can think of off the top of my head would be we do have options in GPSX to do oxygen intrusion at the surface. If you're trying to have an anoxic tank, but there's a little bit of air just comes through the surface, that is a function of mixing and various other things. And these parameters are used in that sense. So therefore, they would be temperature dependent. The most important one, or the most significant one that I usually pay attention to, is the DO saturation. So this is the concentration at full saturation for oxygen. By the way, actually, all of our gases that we model in GPSX also do this. I'm just going to talk about DO because it's the most relevant for the activated sludge process. But, for nitrogen gas and methane and all the other stuff, this is also the same thing here. So let's take a look at how we calculate that. So the saturation concentration is this thing here, C star infinity. And you can see that it is basically taking the value of saturation at 20 degrees and then multiplying it by some correction factors and so on. This is actually dependent on many things, including temperature and depth and so on. So what we're doing is we're coming up with a number here that said for our field conditions, that saturation value could be different depending on what the temperature is. Now, why is that important? That is important because it is part of the driving force that brings oxygen into the liquid so that the biomass can use it. So now this is the mass balance equation that we do in all of our completely mixed tanks. And this is basically trying to figure out exactly how much oxygen is going to, for the next time step, is it going to go up or down? This is the amount coming in. This is the amount going out. We have the amount added by the aeration system, and then the biological reactions, which can usually consume it for that most part. Now, it's actually this part that we're really interested in, these two values. So the KLA is, in this case, the oxygen mass transfer coefficient. And then this part here is that saturation term that I was just mentioning. So the driving force is the difference between what is saturation right now and what is the liquid in the tank. So if this is like, say, 9 milligrams per liter, and this is like 4 milligrams per liter, there'll be a certain driving force multiplied by the KLA that will bring in more oxygen. So the bigger the gradient, the faster the oxygen can be injected into that system. So if this is higher or lower, depending on the temperature, then that could be a significant effect. Now, the other thing is the KLA value is also a function of temperature too. And it is corrected with something very much like the Arrhenius equation here. So we can see it's the KLA value, the mass transfer coefficient at 20 degrees Celsius multiplied by theta over T minus 20. So this is basically the same thing we do for the biological parameters, except it sort of has its own value of theta and so on. So that means ultimately that there's a lot going on with temperature in the aeration model. In fact, some of it kind of works together, some of it works opposite to each other. And I do recommend that if you're really interested in getting into the weeds with those details, that we did a whole webinar on the modeling of aeration systems in GPSX, where we do both mechanical and diffused aeration. And we talk about all of this stuff. I stole these slides out of one of my other slideshows. So hop over to our YouTube channel and take a look at that if you'd like to see that in more detail. Okay, so to summarize for our aeration system, at colder liquid temperatures, the oxygen saturation concentration goes up. So that means our driving force is increased. However, the mass transfer coefficient decreases with the colder temperature. Now, which one of these effects kind of outweighs the other one is a function of many things, but we'll see by playing around a little bit in our example. In addition to all of that, that's just doing the mass transfer part. We want to convert that over to airflow. The airflow calculations, by getting from KLA to airflow and vice versa, are also temperature dependent because one of the terms in there is the density of the air, which is a function of temperature. So you've got sort of the temperature levers on all these different terms and all of these different equations. They're all doing their own thing, and the kind of the sum collection of it is what you get when you look at the output from GPSX. Now, the good thing is we have a lot of output menus, and you can dig into those details as you like. Okay, back to the simulation again. So I'm going to go back to that same layout. And actually, I'm just going to use this sensitivity analysis that we ran before. I don't even need to run it again. We're going to look at this oxygen transfer tab. And so as you may recall, what I did was I ran steady state simulations starting at 5 degrees Celsius all the way up to 20. That's what says on the x-axis down here. And there's two things plotted on this tab: oxygen saturation in black and the total standard oxygen transfer rate in red here. So this is SOTR. So basically, this is mass per time of oxygen, and this is the concentration of the saturation level. So you can see here that, first of all, as I mentioned in the slide, that saturation concentration goes down when things get warmer. That means that our driving force is coming down in that particular case. But here you can see that, of course, the actual amount of oxygen being supplied is going up. And so why is that? The reason is because we have a DO controller on here. So this is set up such that it will apply the whatever airflow is required to meet 2 milligrams per liter. And as we go to higher amounts, higher temperatures, the biomass is working harder. It's consuming more oxygen. The oxygen demand is higher. So the DO controllers turn up the airflow, and then that's why this goes up. So the effect would be shown in the way that the aeration would be supplying the air. Maybe under colder temperatures, it doesn't need to supply quite as much air because the DO saturation is higher. It's kind of hard to pick apart all these different effects. Nonetheless, you have the ability to plot a lot of information here. I just wanted to show you that relationship does exist. We're changing nothing but temperature here, and you see how that changes over time. Okay, so let's go back here. One of the other things that is, again, this is, I think, new in the last couple versions of GPSX, or maybe the last few years we've had this, which is to temperature correct for the diffusion constants in the biofilm. This came out of actually a project that we did with where we had a lot of data and the ability to really look at this in detail. And this is with the MABR unit. That's membrane aerated bioreactor. And so we were modeling a pilot study where they had a huge amount of information for us to be able to play around with. But you can see here what I'm talking about is if you go to the mass transport menu and you hit the More button, then you'll see this menu here. This is basically going to be the diffusion of components in water, and in what happens is we then multiply by the biofilm reduction factor. All of this gets corrected for temperature now. In old, I think versions 7 and back, we didn't actually correct those for temperature, but we found that was a useful thing to do to be able to make sure the model's well calibrated. Okay, moving on to our third and final area, which is the chemical temperature effects. I think this is probably the least big effect that you would see in the system, but since it is there, and since we do go to the effort to make sure this works the way that it's supposed to, I did want to bring it up. So the main thing is that the dissociation constants for acids and bases are temperature dependent. So if I just take a brief moment here just to refresh everybody's mind about what I'm talking about here, is in an sort of an acid-base system, like this carbonate system that we have here. When you put carbonic acid in water, it's going to dissociate into these three things here: carbonate, bicarbonate, and carbonic acid. And what pH we stand at is the thing that's going to tell us how much we have of each of these three different kinds, right? So for a pH of 7 here, that's telling us it's going to be mostly bicarbonate and a little bit of H2CO3 and basically nothing of the carbonate. So now, this is all defined by these intersection points, or these pK values here, which is the intersection when these two things are equal to each other. The pK value is sort of like a fundamental chemical property of these particular components. However, they are temperature dependent, so they may move to the left and to the right depending on what our temperature is. So it is not a very big effect, but it's there, and so we've taken the time to put that in the model. So here, I took this photocopy right out of one of my old chemistry textbooks, and you can see here that this is the pK value for the first dissociation, and this is for the second dissociation. And normally, for most wastewater applications, we kind of live in between these things, closer to the 6 than the 10. And you can see here that these things are a function of temperature. And, for the ranges that we're ever going to deal with, and the kind of work that we all do is, probably 10 degrees up to 30. So, it's not a big change, but don't forget that this is a logarithmic type of calculation. So, it does have an effect. Okay, so I'm just going to pop back to our simulation one last time, because I also had a dissociation tab over here. Ready to go. So the two dissociation constants, now I plotted them as their p values so that the units would be easy to read. Otherwise, it would be something like 4 times 10 to the minus 7. So anyway, I've got the p value here. So it starts at like 10, just like it was on that little chart that I was just showing you. And this one down here is like 6.3 or something. So as you may be able to tell, when we went from 5 degrees Celsius to 20, it's a very slight downhill trend here. And same thing on this one as well. So as I mentioned, it's not going to be a huge effect in your model, but maybe, depending on how close you are. So here, this red is the actual pH of that sensitivity analysis that we just did. And in case you're wondering what's going on here, why is there that bump there? If I just go back to our sensitivity analysis page, you can see that that's basically the point in which nitrification kicked in. So what it's saying is that there's not really any effect on pH until nitrification started, and then suddenly it brought it way, down from, let's see, 7.048 down to 6.6. So, getting close to half a pH unit there when it started and got going at full nitrification. Okay, so that's basically that effect. I'm going to come back to the slides here, and I will mention we do have that one unit process object where we actually predict the temperature for you. Previously, I was saying everything else is a case where you have to tell us the temperature. So in this one, this is a special unit. It's called the Open Basin High Purity Oxygen. And this is a system that runs at a much higher temperature than regular activated sludge. It is a case where we're injecting high purity oxygen gas in with this mixer below the surface in an open basin. So it's kind of a very specialty type of technology. We had some projects where we worked with this vendor. That's where the model came from. And temperature was a real key aspect of this. So we went to that extra level to create its own temperature model. And in this case, you'll notice that it has a lot more parameters related to temperature than your average one in GPSX. And you'll see that essentially we're doing a heat balance in addition to everything else in this particular unit. So we're losing heat through the, the walls and the side and the top and so on. So we have to keep track of all that. And then when you're running the simulation on top of everything else, you get this menu too, these temperature modeling things. And we do get the ability to estimate what we think the temperature will be based on the injection of the gas and the biological activity and so on. And there's a whole kind of like enthalpy balance going on here. That's basically, what was required for this particular project. So that's part of this. Okay, so that's a little bit of a sidebar. Oh, by the way, it does use this different Arrhenius relationship. So this left-hand part is the same thing that we use in most cases, but there's a second part here starting at 35 degrees Celsius where it drops off quite a bit. So this being that, when you get up past a certain temperature, then the temperature itself becomes, a detriment to the biomass growing, and they can't kind of keep increasing forever. So they eventually, their growth starts to drop off. And we have this relationship. We've used this actually in a couple of industrial projects as well, where they were doing, I guess, what you would call conventional activated sludge, but they were doing it at an extremely high temperature. And so we were able to use this relationship in the conventional activated sludge system as well, just to do some interesting things. Okay, so that's a kind of a cover of, I know that's a real sort of scatter shot of a whole bunch of different things, but it is a sense of wanting you to understand all the things in the background that are being adjusted by temperature when you make that, so you pop that one number in the menu there. So it's important to know that there are a few things that are not adjusted for temperature, right? So these are things that aren't directly adjusted for temperature, and I get this question all the time. The settling parameters are definitely not a function of the temperature. To be able to do that, to make the settling parameters a function of temperature, is a much, much, much higher level of modeling than we would be able to do with the regular approaches that we have in GPSX. So that's really about temperature gradient. You got cold things mixing with warm things and densities and falling. So that's kind of a CFD kind of modeling issue. So a lot of the biofilm things that are there, like attachment and detachment, those are not a function of temperature. The energy calculations are, of course, responding to changes in temperature, but they themselves are not, temperature dependent. And pretty much all of our solid separation calculations, like when we're doing, centrifuge and so on, that's not really a function of temperature in any meaningful way. However, most of these things are indirectly dependent on temperature, meaning that temperature will cause more biomass growth, which then gives more airflow, which then uses more energy. So there's like there's sort of this chain of events that happens when you increase your temperature in your model. And so you will see changes based on temperature, but they're not something where we're doing it in the actual calculation itself. Okay, so arriving at the end here, I did want to revisit this. This is actually a redo and an update of an old webinar from, I'm thinking probably 10 years ago. The temperature really is one of the most important settings in the model. As you can see, the reach into all these different processes and calculations is pretty standard. And we tend to not think about it always at the front of our mind, because usually when you're setting up a model for the first time, you're more worried about okay, what's the layout? Where do I put the objects on the drawing board? And what's the influent? What's the size of the clarifiers? All of that is physical, tangible things. It's easy to overlook actually getting the right temperature in there. I've had more than one project where I was in the calibration stage and I'm like, this is not fitting at all. And then I remember, oh yeah, I left the temperature at the default. I have to change that. Yeah, so it's easy to do. And also, really, I suggest that if you could use the global one just to start and get things in line, that's kind of the easiest way to get started in that site properties menu. Or if you have a situation where the temperature changes a lot from the front end of the plant to the back end of the plant, then you're going to have to use the individual local settings in each of those objects and have that either go down or up. I've had several projects where it's gone down because we had a very warm wastewater, and that was coming from an industry or some other reason why it was warmer than it probably should have been, and it kind of comes down as it goes through the plant. I've had at least one where it was the other way. It was, coming in, and the biological activity of the plant kind of heated the water up as it was going through. That's a thing. And so you can set those as you go.